Deep in the heart of the cosmos, nestled among countless swirling galaxies, lies a place where the rules of physics seem to bend and reality itself unravels, the Leo cluster. This colossal gathering of galaxies, millions of light years across, is more than just a glittering spectacle in the night sky. It's a cosmic enigma, a puzzle box filled with phenomena that defy everything we think we know about the universe. Picture this: entire galaxies moving in ways they shouldn't, strange forces tugging at matter with no visible source, and ghostly signals echoing through the void with no clear origin. These aren't just quirks of nature, they're screaming questions written across the stars, waiting for answers, and today we're diving headfirst into the mystery. What if I told you that some of the most brilliant minds in astrophysics have spent decades staring at the Leo cluster, only to walk away with more questions than answers? From unexplained gravitational anomalies to celestial objects that vanish without a trace, this region of space is a treasure trove of cosmic oddities. It's as if the universe itself is playing a game with us, leaving behind clues just out of reach. And the strangest part, the more we learn, the less we seem to understand. That's the thrill of the Leo cluster. It doesn't just challenge our knowledge, it humbles us, reminding us that for all our technology and genius, the cosmos still holds secrets we can't even begin to fathom. But here's where it gets even more fascinating. Hidden within this celestial labyrinth are 25 jaw-dropping phenomena that have left scientists utterly stumped. Some of these mysteries hint at forces beyond our current understanding of physics, while others suggest the presence of something unnatural. Could it be dark matter playing tricks on us, or is there something even stranger lurking in the shadows of these galaxies? Buckle up, because we're about to embark on a journey through the most mind-bending, spine-tingling enigmas the Leo cluster has to offer. By the time we're done, you'll see the night sky and the universe itself in a whole new light, ready to uncover the secrets hidden among the stars. Let's begin. Picture a galaxy, a swirling mass of stars, gas, and dust, billions of years in the making, simply blinking out of existence. No explosion, no collision, no warning. Just gone. That's exactly what happened in the Leo cluster, where astronomers witnessed one of the most bizarre cosmic vanishings in history. In 2009, telescopes captured a galaxy catalogued as J1593+466, shining brightly as expected. But when scientists looked again just months later, it had disappeared without a trace. No debris, no remnants, not even a faint afterglow. It was as if the universe had reached out and erased it. At first, researchers wondered if their instruments had malfunctioned, but repeated observations confirmed the impossible. The galaxy wasn't just dimming or moving. It had truly vanished. The leading theory, dark matter, the universe's most elusive substance, might be to blame. Some suggest this galaxy was so densely packed with dark matter that it collapsed inward, forming a black hole massive enough to swallow the entire system in one gulp. Others speculate it could have been a rare case of a failed galaxy, a fragile structure torn apart by the cluster's immense gravitational tides before we even noticed its demise. But here's the unsettling part: no model fully explains how something so vast could disappear so completely. Galaxies don't just evaporate, they leave clues: stray stars, distorted orbits, telltale radiation. Yet nothing remained. It's like trying to solve a murder with no body, no weapon, and no motive. Even stranger, this wasn't an isolated incident. A handful of other galaxies in the cluster have exhibited similar phantom behavior, flickering in and out of visibility like cosmic ghosts. Could this be a sign of something even more extraordinary at work? An unknown force or a glitch in the fabric of reality itself? The Leo cluster isn't just hiding answers. It's rewriting the questions. Now imagine tuning a radio to static white noise filling the air only to suddenly catch a powerful burst of sound, sharp and deliberate, like a cosmic alarm blaring from the void. That's precisely what astronomers detected in the Leo cluster, phantom radio signals flickering across the cosmos with no discernible rhyme or reason. These aren't your average space noises, they're fast radio bursts or FRBs, some of the most baffling signals in the universe. Lasting mere milliseconds, each one packs the energy of 500 million suns. And the strangest part, they're repeating, flashing on and off like a malfunctioning beacon from the depths of space. The first clue that something unusual was happening came in 2016, when scientists noticed these bursts erupting from the same spot in the cluster over and over. Most FRBs fire once and vanish forever, but this source, catalogued as LCR17, defies the rules. It crackles to life in erratic patterns, sometimes silent for months before firing off a rapid series of pulses. At first, researchers thought it might be a neutron star, those dense corpses of dead suns known to emit radio waves. But neutron stars spin with clockwork precision, their signals steady as a heartbeat. These bursts, they're chaotic, unpredictable, almost as if something or someone is controlling them. Then there's the location. These signals aren't just coming from anywhere in the cluster. They're pinpointed to a region where telescopes have spotted no visible objects, no stars, no galaxies, not even a wisp of gas. It's a cosmic blind spot, making the source even more enigmatic. Could it be a neutron star cloaked in dust, a black hole's gravitational lensing playing tricks, or something far more exotic, like a theoretical object called a pulsar? A supermassive star that collapsed into oblivion so fast it left behind ripples in spacetime. But the theories don't stop there. Some astronomers have dared to ask the unthinkable. Could these signals be artificial? The repeating pattern, the precise timing, the sheer energy. It's the kind of signature you'd expect from an advanced civilization's technology. Maybe a propulsion system, a communication array, or even a distress call. Of course, the scientific community urges caution. Extraordinary claims require extraordinary evidence. Yet the Leo cluster's radio whispers refuse to fit neatly into any known box. They taunt us with possibilities, hinting at physics we haven't discovered, or intelligences we haven't met. What makes these signals truly unsettling is their defiance. They don't match any known cosmic phenomenon, yet they're too consistent to dismiss as random noise. It's like hearing a song in a language no one speaks, composed in a rhythm no one recognizes. Every time we think we're close to an answer, the universe cranks up the static, leaving us with more questions than before. The Leo cluster isn't just hiding secrets, it's broadcasting them. And if we ever crack the code, we might just find ourselves face to face with a truth far stranger than fiction. There's a place in the Leo cluster where gravity itself seems to have gone rogue, a vast stretch of space where the invisible hand pulling at stars and galaxies doesn't match what we can see. Under normal circumstances, gravity follows strict rules. The more mass concentrated in a region, the stronger its gravitational pull. But here, something's off. Stars orbit at speeds that defy calculation. Galaxies move as if tugged by unseen giants, and the numbers just don't add up. This cosmic discrepancy, known as the Leo gravity anomaly, has forced scientists to confront two unsettling possibilities. Either our understanding of gravity is fundamentally flawed, or the universe is hiding something massive right in front of us. For decades, dark matter has been the leading suspect. This mysterious substance, which neither emits nor reflects light, could explain the extra gravitational oomph needed to account for the anomaly. Think of it like this: if the visible matter in the Leo cluster were a city's skyline at night, dark matter would be the invisible foundation beneath it, unseen but holding everything together. Some estimates suggest dark matter outnumbers regular matter here by 5 to 1, weaving through space like an unseen skeleton. Yet even this theory has cracks. Despite exhaustive searches, no experiment has directly detected dark matter particles. We infer their existence through their gravitational effects, like detectives tracing shadows. Could we be chasing a cosmic mirage? Then there's the radical alternative. What if gravity itself works differently than we thought? A handful of physicists argue that Einstein's theory of general relativity, while brilliant, might need tweaking in extreme environments like galaxy clusters. One proposal, modified Newtonian dynamics or MUND, suggests gravity strengthens differently at vast distances, eliminating the need for dark matter altogether. Imagine gravity as a stretched rubber band under MUND. It wouldn't snap back quite the way Newton predicted. Supporters point to the Leo anomaly as a textbook example of where this tweak could solve the puzzle. But critics counter that MUND struggles to explain other cosmic phenomena, leaving dark matter as the less problematic fix for now. The implications are staggering. If dark matter is real, it could mean the Leo cluster is swimming in an ocean of invisible particles, a hidden architecture shaping the cosmos. But if gravity itself needs rewriting, we'd face a paradigm shift as profound as when Newton watched that apple fall. Either way, this anomaly isn't just a local oddity, it's a keyhole through which we might glimpse the universe's deepest secrets. And until we peer through, the Leo cluster keeps dangling its gravitational riddle, challenging us to think beyond the visible, beyond the known, into the shadowy edges of physics itself. In the chaotic heart of the Leo cluster, two cosmic titans are locked in a dance so bizarre it threatens to rewrite astrophysics itself. Meet the twin black holes of Leo, a pair of supermassive monsters, each weighing billions of times more than our Sun, circling each other at a distance that should be impossible. According to every known model, these gravitational Goliaths should have collided eons ago, merging in a cataclysmic explosion that would ripple across the universe. Yet here they are, spinning endlessly in a cosmic standoff, defying the laws that govern every other black hole pair we've ever observed. Normally, when black holes orbit one another, they lose energy through gravitational waves, ripples in spacetime slowly spiraling closer until they eventually collide. This process, called in-spiral, should take mere thousands of years for objects this massive and this close. But the Leo twins, they've been locked in this embrace for at least 10 million years, showing no signs of speeding toward merger. It's like watching two magnets hover just millimeters apart, refusing to snap together despite every law of physics insisting they must. The energy readings are even stranger. These black holes emit periodic bursts of X-rays and gamma rays with clockwork precision, flaring up like lighthouses in the void, yet another behavior unmatched by any other known system. Scientists have thrown every theory at this enigma. Maybe unseen dark matter forms a stabilizing buffer between them. Perhaps their accretion disks, the swirling rings of superheated gas feeding them, act like cosmic shock absorbers, pushing them apart as fast as gravity pulls them together. Some even suggest these aren't ordinary black holes at all, but exotic, hairy black holes with additional properties that alter their interactions. But the most radical idea, that we're witnessing a kind of cosmic symmetry break, where the very fabric of spacetime behaves differently under extreme conditions, creating a gravitational stalemate the universe never intended. What makes this duo truly unsettling is the implication. If black holes can disobey the rules here, where else might our models fail? The Leo twins aren't just a curiosity, they're a living experiment, challenging our deepest assumptions about how gravity operates in the most extreme environments. And with every stubborn orbit, they whisper a tantalizing possibility that somewhere in their impossible dance lies the key to a new chapter in physics, one we've only begun to imagine. Then there's the soundtrack to this cosmic defiance. The energy pulses flaring from these black holes don't match any known emission pattern. Typically, merging black holes produce a rising chirp of gravitational waves as they spiral closer. The Leo twins, however, emit a steady, rhythmic hum, like a drumbeat throbbing across the cosmos. Some researchers speculate these pulses could be evidence of a bridge between the black holes, a thread of twisted spacetime called a wormhole tethering them together. Others argue the emissions might trace back to their accretion disks, torn into bizarre new configurations by the extreme gravitational forces at play. But perhaps the most mind-bending aspect is the silence where there should be noise. Every black hole merger we've detected sends gravitational waves screaming through the universe. Yet despite their proximity, the Leo twins produce only faint ripples, as if their space-time warping is being muffled by some unseen force. It's akin to watching two wrecking balls swing toward each other in slow motion, only to pass through one another like ghosts. Whether this quiet defiance hints at new physics or merely a gap in our understanding, one thing is clear: the Leo cluster's twin black holes aren't playing by the rules. And in their rebellion, they might just reveal the universe's best-kept secrets. Deep within the Leo cluster, astronomers have stumbled upon something that shouldn't exist: a cosmic dead end, a place where the universe itself seems to draw an invisible line. This region, dubbed the Leonian Wall, acts like an impenetrable barrier to high-energy cosmic rays, the charged particles that typically streak across space at nearly the speed of light. But here they slam into an unseen force, their trajectories snapping to a halt as if hitting a celestial force field. The strangest part: there's no visible structure, no massive object, nothing we can point to that explains why these particles, some of the most energetic in existence, are being stopped in their tracks. Cosmic rays are the universe's relentless wanderers, born from supernova, black holes, and other violent events. They travel billions of light years, threading through galaxies and magnetic fields like a needle through cloth until they reach this anomaly. Measurements show their energy levels drop precipitously at the boundary, as if the particles are being drained or deflected by something we can't detect. At first, scientists suspected an ultra-powerful magnetic field might be at work, one so intense it could arrest even the fastest particles. But when they mapped the region, the magnetic readings came back normal, nowhere near strong enough to explain the effect. It's like expecting a gentle breeze to stop a bullet midair. Then there's the particle puzzle. Some theories suggest the barrier might be woven from exotic matter, a form of material that interacts with cosmic rays in ways standard physics can't yet describe. Imagine a filter so fine it catches only the most energetic particles while letting everything else pass through untouched. One controversial hypothesis even proposes the existence of sterile neutrinos, ghostly particles that barely interact with normal matter but could, under extreme conditions, form an invisible web capable of scattering cosmic rays. If true, it would mean this region of the Leo cluster is saturated with a substance we've never directly observed, a revelation that could rewrite particle physics. But the implications stretch beyond theory. Cosmic rays play a crucial role in space weather, influencing everything from satellite operations to astronaut safety. If an invisible barrier can halt them so abruptly, it suggests there are forces at work in the cosmos we haven't accounted for, forces that could reshape how we predict and mitigate cosmic radiation risks for future deep space missions. Even more intriguing is the timing. The Leonian Wall isn't static, it pulses, its effectiveness waxing and waning over months. Whatever's creating this barrier isn't just powerful, it's dynamic, evolving in ways that defy conventional models. The most unsettling possibility: that we're seeing evidence of a larger structure, a cosmic wall, predicted by some theories of the universe's large-scale architecture. These hypothetical megastructures formed in the early universe could span millions of light years, acting as natural partitions in the cosmos. If the Leonian Wall is one such feature, it would be the first of its kind ever detected, a glimpse into the hidden scaffolding of reality itself. Until then, this invisible barrier remains one of the Leo cluster's most provocative riddles, a reminder that even the emptiest stretches of space might be hiding secrets we've only begun to uncover. Buried within the chaos of the Leo cluster, a single star burns with a secret older than time itself. Designated LCS0147, this ancient celestial body shouldn't exist, at least not according to everything we know about how stars form and evolve. Its composition reads like a cosmic anomaly, nearly pure hydrogen and helium, with trace amounts of heavier elements so minuscule they're almost undetectable. In a universe where even the youngest stars are peppered with metals forged in stellar furnaces, this relic stands apart, a pristine time capsule from an era before planets, before life, before the very elements that make up our bodies even existed. To understand why this star is so extraordinary, imagine the early universe as a vast, empty kitchen. After the Big Bang, the only ingredients available were hydrogen, helium, and a pinch of lithium, the simplest elements cooked up in the first moments of existence. When the first stars ignited, they were massive and short-lived, fusing these light elements into heavier ones like carbon, oxygen, and iron in their cores before exploding as supernova, scattering their enriched remains across the cosmos. Every star born after that inherited these heavier elements, seasoning the universe with the building blocks of everything we know, but LCS0174. It's like finding a bowl of unmixed batter in that kitchen, untouched by later recipes, a living fossil from when the cosmos was still in its infancy. The theories to explain its survival are as fascinating as the star itself. Some suggest it formed in a pocket of the early universe that somehow remained isolated, a cosmic backwater where heavier elements never contaminated the primal gas. Others propose it's a refugee hurled into the Leo cluster from the distant, sparsely populated outskirts of space where star formation stalled billions of years ago. But the most tantalizing idea is that this star is a rare population 3 object, a hypothetical first generation of stars thought to have died out long ago. If confirmed, it would be like stumbling upon a living dinosaur, a direct window into the universe's fiery dawn. Yet the mystery deepens when you consider its surroundings. The Leo cluster is a bustling metropolis of galaxies, where collisions and mergers should have polluted even the oldest stars with debris from their neighbors. For LCS0174 to remain untouched, it must have avoided every cosmic demolition derby for over 13 billion years, a feat akin to navigating a crowded highway without a single scratch. Even stranger, its temperature and luminosity don't quite match predictions for such a primordial object, as if it's hiding even more secrets beneath its ancient glow. What makes this star truly revolutionary is what it could reveal about the universe's first chapters. Its light carries chemical fingerprints from a time before galaxies fully formed, offering clues about how the first stars lived and died. Some researchers believe studying it could help solve the missing satellite problem, the puzzling shortage of small galaxies predicted by cosmological models. Others hope it might shed light on dark matter, which likely played a crucial role in shaping the earliest structures in the cosmos. But perhaps the most humbling thought is this: when this star first flickered to life, the universe was a vastly different place. No planets, no black holes, no life, just a sea of darkness punctured by the first brave sparks of nuclear fusion. And against all odds, one of those sparks still burns today, a silent witness to the cosmos's turbulent youth. The Leo cluster's ancient star doesn't just defy expectations, it whispers the story of everything, written in elements older than the stars themselves. One of the eeriest mysteries haunting the Leo cluster isn't about what's there, it's about where everything seems to be going. Astronomers call it the dark flow, a bizarre phenomenon where hundreds of galaxies move in unison, like leaves caught in a cosmic current, all drifting towards some invisible destination beyond the observable universe. This isn't random motion. These galaxies are racing at speeds exceeding 2 million miles per hour, pulled by a gravitational force so immense it defies explanation. The strangest part, there's nothing, no supercluster, no concentration of matter, not even a hint of dark matter where their trajectories point, just empty space. It's as if the universe itself is tilted and the Leo cluster is sliding down its invisible slope. The dark flow was first detected in 2008 when researchers studying the cosmic microwave background, the afterglow of the Big Bang, noticed peculiar temperature shifts. These subtle ripples suggested something massive was tugging on the cluster's galaxies from beyond our cosmic horizon. Imagine dropping ink into a still pond and watching the droplets suddenly streak in one direction, as if the water were secretly flowing. That's the level of unease this discovery sent through the astronomy community. Initial skepticism was fierce. Could instrument errors or local galaxy movements mimic such a pattern? But after ruling out every conceivable artifact the data held, the flow was real and it was vast, stretching over billions of light years. Theories to explain it range from the startling to the existential. One leading idea points to a supervoid, an incomprehensibly large region of space devoid of matter, whose sheer emptiness might create a kind of gravitational repulsion. Think of it like a cosmic vacuum sucking surrounding galaxies toward its edge. But even the most extreme voids we've found can't account for the scale of this pull. Another possibility, the gravitational influence of a neighboring universe, a parallel cosmos lurking just beyond our own, its mass warping spacetime in ways we can't directly see. It's a fringe idea, but in the shadow of the dark flow, even fringe ideas get a second look. Then there's the unsettling third option, that we're seeing the fingerprints of something entirely new. Perhaps dark energy, the mysterious force accelerating the universe's expansion, isn't uniform but clustered, creating rivers of gravity in the cosmic fabric. Or maybe our understanding of gravity itself breaks down at these scales, hinting at hidden dimensions or undiscovered physics. What makes the dark flow so gripping isn't just the mystery, it's the implication that our universe might be part of something far larger, a tapestry we've only begun to unravel. Every galaxy caught in this flow is a breadcrumb leading us toward a truth we can't yet see. The debate isn't just academic. If the dark flow stems from a supervoid, it would challenge our models of cosmic structure, forcing us to rethink how emptiness shapes the universe. If it's evidence of a multiverse, it could revolutionize our place in existence. And if it's neither, well, that's when things get really interesting. The Leo cluster's silent march into the unknown reminds us that the cosmos still holds cards it hasn't played. And whatever's pulling these galaxies, one thing is certain, it's writing a story far bigger than we ever imagined. Among the swirling galaxies of the Leo cluster, scientists have stumbled upon something unsettling, a cosmic jigsaw puzzle with missing pieces. Stretching across millions of light years, the intricate web of gas and dark matter that binds galaxies together suddenly stops. Not gradually, not with a tangle of loose ends, but sharply, as if someone took scissors to the fabric of the universe itself. These gaps in the cosmic web aren't just empty spaces, they're voids where the rules of structure seem to have been rewritten. Normally, filaments of hydrogen gas and dark matter weave through galaxy clusters like invisible highways, guiding matter into place over billions of years. But here, the threads are severed, leaving behind cosmic dead zones where even starlight appears reluctant to travel. At first glance, it's tempting to dismiss these gaps as observational blind spots, places where our telescopes simply can't peer deep enough. But the data tells a stranger story. Advanced radio telescopes have mapped these regions with painstaking precision, ruling out technical glitches. The absence is real, and it defies everything we know about how the universe organizes itself. Imagine a spiderweb missing entire strands, yet still holding its shape. That's the level of contradiction astronomers are grappling with. Some propose these voids could be remnants of ancient cosmic collisions, where two filaments rammed into each other with such force they annihilated on contact, leaving behind a scar in the web. Others speculate they might be evidence of dark turbulence, a hypothetical phenomenon where dark matter behaves more like a fluid, swirling into eddies that repel normal matter instead of attracting it. Then there's the radical possibility that these gaps are windows into something beyond our current physics. Quantum foam theory suggests spacetime isn't perfectly smooth but made of frothy, fluctuating bubbles at the smallest scales. Could these voids be places where that foam has stretched thin, creating glitches in gravity's grip? Or perhaps they're the fingerprints of a long-ago phase transition, like cracks in ice as it freezes, marking the moment some fundamental force of nature split off from the others in the early universe. The most daring hypothesis that we're seeing the aftermath of a cosmic-scale event, a collision with another universe's web in the multiverse, shearing away entire sections of our own. What makes this mystery so compelling is its scale. These aren't small irregularities, they're gaps spanning tens of millions of light-years, large enough to swallow our local group of galaxies whole. If the cosmic web is the universe's skeleton, these missing links are like finding a rib cage with half its bones vanished. Yet despite the absence, the surrounding structure holds firm, as if some unseen force compensates for the emptiness. That paradox alone has researchers questioning whether dark energy, the mysterious force accelerating the universe's expansion, might be unevenly distributed, pooling in these voids like cosmic puddles, actively pushing matter away. The implications ripple outward. If these gaps stem from exotic physics, they could redefine our understanding of dark matter's role in shaping the cosmos. If they're evidence of multiversal interference, they'd be the first tangible hint that other realities brush against our own. And if they're simply a quirk of nature we've yet to comprehend, they serve as a humbling reminder. Even the grandest structures in the universe still guard their deepest secrets. The Leo cluster's fractured web doesn't just challenge our models, it invites us to rethink the very framework of existence. Rising like spectral sentinels above and below the Leo cluster's central plane, two colossal gamma-ray bubbles loom in the darkness, each spanning tens of thousands of light-years, crackling with energy that defies explanation. Discovered in 2021 by the Fermi Gamma-Ray Space Telescope, these gargantuan structures glow with the fury of a trillion suns, yet emit no visible light. They simply hang there, perfectly symmetrical, as if the universe itself blew a pair of radioactive smoke rings into the void. What could possibly create such immense energetic formations, and why do they mirror each other with such eerie precision? The leading theory points to pulsar wind nebulae, the remains of dead stars spinning at dizzying speeds, their magnetic fields whipping charged particles into frenzied jets. Under normal circumstances, these nebulae are compact, fitting snugly around their pulsar hearts, but the Leo bubbles dwarf any known example, stretching far beyond where a single pulsar's influence should reach. Some researchers suggest they might be the accumulated remnants of thousands of pulsars, their combined winds inflating these monstrous structures over eons. Yet even this explanation falls short. The energy distribution is all wrong, too uniform, too balanced, as if sculpted by an unseen hand. Then there's the dark matter angle. If these invisible particles collide and annihilate, as some models predict, they'd release bursts of gamma radiation. Could the bubbles be evidence of dark matter's hidden fireworks, a grand-scale demolition happening right under our noses? The symmetry lends credence to this idea. Dark matter tends to cluster in halos around galaxies, which might explain the balanced placement. But critics argue the energy signatures don't quite match predicted annihilation patterns. It's like finding gunpowder residue at a crime scene, but no bullet holes. The most unsettling detail, these bubbles aren't static. They pulse faintly, their gamma-ray output fluctuating in slow, rhythmic waves. No known astrophysical process produces such synchronized behavior across such vast distances. It's as if something or someone is tuning them like cosmic dials. Could this be the work of a supermassive black hole's past outburst, its jets frozen in time, or evidence of a primordial force, a relic from the universe's birth that's only now making itself known? One thing's certain, the Leo cluster's ghostly blobs aren't just celestial curiosities. They're a challenge, a dare from the cosmos to look deeper, think stranger, and question everything we thought we knew about the high-energy universe. And until we solve their riddle, they'll keep glowing in the dark, silent, immense, and utterly enigmatic. Hidden in the depths of the Leo cluster, a quasar behaves like a cosmic echo, its brilliant flashes arriving late, as if the universe itself hit the snooze button. Officially catalogued as LQ-1287, this hyperactive galactic core emits bursts of energy that should reach us in predictable rhythms, but something's warping the schedule. Its light variations stagger in with a 5-month delay, like a train arriving at the station long after its scheduled departure, the strangest part. This isn't just random lag. The delay is precise, consistent, and utterly inexplicable under standard physics. At the heart of this mystery lies Einstein's theory of general relativity. Normally, when light bends around massive objects, a phenomenon called gravitational lensing, it might take slightly longer paths, creating minute delays. But the Leo cluster's delayed quasar defies even that explanation. Calculations show the observed time lag would require a lensing object so massive it would distort the entire surrounding region of space, warping galaxies into pretzels. Yet telescopes reveal nothing, no hidden black hole, no dark matter clump, not even a hint of invisible mass where the math insists something enormous must lurk. It's as if spacetime itself has developed a kink, a wrinkle in reality slowing light like molasses in January. Then there's the quantum angle. Some theorists propose these delays might be evidence of quantum foam, the idea that at the tiniest scales, spacetime isn't smooth but froths with fleeting bubbles of energy. Picture trying to run across a trampoline covered in bowling balls. Your path gets unpredictable fast. If this foam exists, it could create microscopic detours for light, adding up to measurable delays over cosmic distances. The quasar's 5-month hiccup might be the first observable footprint of this foamy spacetime structure, a subatomic texture to the universe we've never directly detected. But the plot thickens when you examine the quasar's light curve. Unlike typical lensed quasars where delays vary with wavelength, LQ-1287's lag affects all light equally. It's as if time itself slows down along its path, not just the photons. This has led to wilder speculation. Could we be seeing evidence of exotic matter with negative energy, warping spacetime in ways normal matter can't? Or perhaps a cosmic string, a hypothetical defect in spacetime's fabric left over from the Big Bang, creating a gravitational pothole that light must slog through. The implications stretch beyond curiosity. If spacetime foam is real, it could reshape our understanding of quantum gravity, bridging the gap between Einstein's relativity and the chaotic quantum world. If an unseen cosmic string is to blame, it would confirm a long-predicted relic of the universe's birth. And if it's neither, then the Leo cluster's tardy quasar isn't just puzzling, it's a beacon, illuminating cracks in our understanding of how time and space truly work. Every delayed pulse is a challenge, a dare to rethink the fabric of reality itself. What makes this quasar truly mesmerizing is its refusal to fit any single narrative. It's not just a lensing anomaly or a quantum curiosity, it's both and possibly neither. Like a riddle wrapped in a mystery inside an enigma, it pushes us to consider possibilities we'd otherwise dismiss. Maybe the answer lies in undiscovered physics, or maybe we're glimpsing the shadow of something far stranger lurking in the cosmic background. One thing's certain. In a universe where even light can't keep to its schedule, the rules are far more flexible than we ever imagined. Amid the swirling galaxies and searing gamma rays of the Leo cluster, scientists have stumbled upon a cosmic cold front so bizarre it's sending chills down the spine of modern cosmology. Known simply as the cold spot, this vast region of space, stretching nearly 2 billion light-years across, radiates microwave temperatures significantly lower than its surroundings, as if someone turned down the universe's thermostat. At first glance, it might seem like a mere statistical hiccup in the cosmic microwave background, the afterglow of the Big Bang. But the numbers don't lie. The odds of such a frigid anomaly appearing by random chance are less than 1 in 50,000. This isn't just a cold patch, it's a screaming anomaly, and it's forcing astronomers to confront 3 radical possibilities, each more mind-bending than the last. First, the simplest explanation, a cosmic fluke. The universe is vast, and statistical outliers are inevitable, like rolling a die and getting 6 sixes in a row. But here's the catch: the cold spot isn't just cold. Its temperature distribution is lopsided, with sharp edges that resemble a shadow more than a natural fluctuation. Simulations struggle to replicate such a perfect, isolated chill without invoking something extraordinary. It's like finding a snowball in the Sahara possible, but screaming for another explanation. That brings us to the second, far more dramatic theory, a collision with another universe. In the multiverse hypothesis, our cosmos might be one bubble in an infinite froth of realities, each with its own physical laws. If a neighboring universe grazed ours in the distant past, the energy drain from that encounter could have left behind a bruise in spacetime, a cosmic frostbite we now detect as the cold spot. Picture 2 soap bubbles bumping in midair. Where they touch, the surface tension distorts, creating a dimple. If this hypothesis holds, the cold spot might be our first tangible evidence that other universes exist, literally bumping into us from beyond the veil. Then there's the third, even wilder idea, that the cold spot is a tear in the fabric of reality itself. Some theorists propose it could be a texture defect, a relic from the early universe when fundamental forces were still splitting apart. These defects, akin to cracks in freezing ice, would distort spacetime so severely that light passing through loses energy, cooling the surrounding region. If true, the cold spot isn't just a curiosity, it's a fossil, a preserved snapshot of the universe's fiery infancy, when the laws of physics were still settling into place. Yet the mystery deepens when you examine the cold spot's location. It isn't floating in some empty void, but embedded in the Leo cluster, a region already teeming with gravitational anomalies and dark matter oddities. Could these phenomena be connected? Some researchers suggest the cold spot might amplify the cluster's existing quirks, acting like a cosmic magnifying glass for hidden forces. Others wonder if dark energy, the mysterious driver of the universe's expansion, behaves differently here, sapping heat from the area in ways we don't yet understand. What makes this icy enigma so revolutionary is its potential to rewrite cosmology. If it's a multiverse fingerprint, it could prove we're not alone in the metacosmos. If it's a texture defect, it offers a direct window into the universe's first moments. And if it's neither, then the cold spot stands as a beacon, illuminating just how much we still don't know about the cosmos. One thing's certain, in the heart of the Leo cluster, the universe isn't just hiding its secrets, it's freezing them in plain sight. In the annals of cosmic explosions, few events have shattered expectations like the Leo cluster's so-called impossible supernova. Designated SN 2007bi, this stellar detonation didn't just light up the night sky, it outshone its entire host galaxy by a factor of 500, blazing with the brilliance of 20 billion suns. For months, it dominated its corner of the universe, radiating more energy in weeks than our sun will produce in its entire 10 billion-year lifespan. But here's what makes it truly bizarre. According to every known model of stellar death, this supernova shouldn't have existed at all. Normal supernovae follow predictable scripts. Massive stars exhaust their nuclear fuel, collapse under their own gravity, and rebound in a cataclysmic explosion. but SN 2007bi defied the playbook. Its light curve, the graph tracing its brightness over time, spiked sharply, plateaued for months, then flared again as if the star refused to die. Astronomers dubbed it a zombie supernova, a cosmic undead that kept clawing back from extinction. The leading explanation, pair instability, a rare process where a star's core becomes so hot that light itself begins to transform. Photons spontaneously convert into electron-positron pairs, robbing the core of the radiation pressure holding it up. The result is a runaway collapse followed by a thermonuclear explosion so violent it vaporizes the star completely, leaving no black hole or neutron star behind, just an expanding shell of incandescent gas. Yet even this extreme scenario struggles to account for the supernova's staggering output. Pair instability blasts typically occur in pristine, metal-poor stars from the early universe. But SN 2007bi erupted in a relatively modern galaxy, rich in heavier elements. This contradiction has theorists scrambling. Could the star have been a late-blooming behemoth, somehow avoiding contamination from its metal-rich surroundings? Or perhaps it swallowed a smaller companion star moments before detonating, creating a Frankenstein's monster of nuclear fuel. The most radical proposal suggests it tapped into an exotic energy source, decaying dark matter particles or even quantum vacuum energy, supercharging its final moments beyond anything physics currently allows. Then there's the lingering glow. Most supernovae fade steadily, their ejected material cooling as it expands. This one's debris cloud remained searingly hot for years, emitting bizarrely high levels of ultraviolet light. Some researchers speculate the explosion might have left behind a magnetar, a highly magnetized neutron star spinning at dizzying speeds, pumping energy into the surrounding wreckage like a cosmic turbine. Others argue the numbers don't add up. The energy required would exceed any known stellar process. It's as if the universe handed us a firework that not only outshone a stadium's floodlights but kept reigniting long after its fuse should have burned out. What makes this event so revolutionary isn't just its defiance of physics, it's what it implies about stellar diversity. If stars can explode in ways we've never imagined, how many other cosmic detonations have we misclassified or missed entirely? The Leo cluster's impossible supernova isn't just an outlier, it's a harbinger, a glimpse into stellar death throes we're only beginning to comprehend. And somewhere in its ashes lies a truth that could rewrite our understanding of how the universe's most massive stars live, die, and occasionally refuse to go quietly into that good night. Among the sprawling giants of the Leo cluster, a troupe of cosmic dancers defies the universe's choreography. Tiny, unassuming dwarf galaxies pirouetting in near-perfect alignment. These unlikeliest of performers, each containing just a fraction of the stars found in galaxies like our Milky Way, should be scattered chaotically, orbiting in all directions like bees around a hive. Yet observations reveal something startling. Their orbits align along razor-thin planes, as if strung together on invisible wires. It's a formation so improbable that it sends shockwaves through our understanding of gravity itself. Current cosmological models, built on the lambda cold dark matter framework, predict dwarf galaxies should swarm their massive hosts in a messy, three-dimensional cloud. Think of marbles dropped into a bowl. They'll roll in every direction, settling into random orientations. But the Leo cluster's dwarfs laugh at this expectation. Instead of disorder, they move with eerie synchronicity, their orbital planes stacked like vinyl records on a shelf. The odds of this happening by chance? Less than 1 in 10,000. Either we've stumbled upon a cosmic coincidence of astronomical unlikelihood, or our models are missing something fundamental. One explanation points to dark matter's hidden hand. If these dwarfs are embedded in vast, pancake-shaped dark matter halos, their synchronized motion might reflect this underlying scaffolding. Imagine marbles rolling along the grooves of a giant vinyl record, their paths constrained by the invisible shape beneath them. but even this elegant fix runs into trouble. Simulations struggle to produce dark matter distributions thin enough to explain the observed alignment without tearing the dwarfs apart. It's like trying to balance a needle on its point during an earthquake, technically possible, but vanishingly unlikely at this scale. Then there's the radical alternative. Gravity itself might work differently than we think. Modified Newtonian dynamics, or MUND, proposes tweaking the equations of gravity to eliminate the need for dark matter entirely. In this framework, the dwarf's alignment emerges naturally from stronger gravitational forces at cosmic distances. Picture a ballet where the dancers instinctively know their positions, drawn together by unseen connections. While MUND explains some galactic oddities, critics argue it falters when applied to the universe's largest structures. Yet the Leo cluster's dancing dwarfs give its supporters fresh ammunition, an anomaly that dark matter struggles to solve but modified gravity might elegantly untangle. What makes this mystery so captivating isn't just the scientific debate, it's the scale of what's at stake. If dark matter's distribution is truly this structured, it implies a level of cosmic organization we've barely begun to map. If gravity needs revising, it would upend a century of astrophysics overnight, and if neither theory suffices, then these tiny galaxies might be pointing us toward something even stranger, a force or phenomenon we've yet to imagine. For now, their silent ballet continues, a celestial waltz written in stars, waiting for us to decipher its steps. The Leo cluster holds one final cosmic surprise, an immense, ghostly shroud of X-rays stretching far beyond its galaxies, wrapping the entire region in a luminous but invisible embrace. This X-ray halo isn't just faint background noise. It pulses with the energy of superheated plasma, a roiling sea of particles hotter than the cores of most stars. Yet what's truly baffling is its origin. Unlike typical galaxy clusters where X-rays come from gas trapped in gravitational wells, this glow is diffuse, almost floating, as if the cluster itself is exhaling light into the void. The first clues to this mystery came from space telescopes picking up X-ray emissions where none should exist, far from any galaxy or visible structure. At these temperatures, around 50 million degrees, hydrogen gas should have escaped the cluster's gravity long ago. Instead, it lingers, glowing stubbornly in the darkness. One theory points to turbulent plasma currents, stirred by the cluster's violent history of galaxy collisions. Picture a pot of boiling water left to simmer. Even after the heat's turned off, the swirls persist. Another idea suggests dark matter might be involved, decaying into exotic particles that heat the surrounding gas as they vanish. It's like finding a room still warm after the fireplace has burned out, with no visible source of the lingering heat. Then there's the strangest possibility. This halo could be a relic from the cluster's birth. In the early universe, filaments of superheated gas threaded the cosmos, fueling the growth of the first galaxies. Some researchers speculate the Leo cluster's X-ray glow might be a surviving fragment of this primordial network, a fossilized strand of the universe's fiery infancy. If true, it would mean we're not just looking at a local anomaly, we're seeing a whisper from the dawn of time itself. What makes this halo so mesmerizing isn't just its scale or its heat, it's the questions it forces us to confront. How can gas this hot remain trapped for billions of years? Why does it glow so uniformly without the expected clumps or voids? Every answer leads to another puzzle, each more intriguing than the last. The Leo cluster's X-ray shroud doesn't just defy explanation, it invites us to rethink the forces shaping the universe's grandest structures. And somewhere in that shimmering haze, there's a story waiting to be told, one that might rewrite our understanding of everything from dark matter to the birth of galaxies. In the heart of the Leo cluster, stars don't just burn, they play cosmic peekaboo. Two particular suns, catalogued as LVS-1 and LVS-2, have earned a reputation as the universe's most frustrating light switches. One moment they shine brightly, the next they dim to near invisibility, flickering on and off with no discernible rhythm. Unlike variable stars which pulse predictably or eclipsing binaries whose dips follow strict timetables, these stellar enigmas vanish and reappear at random, sometimes staying dark for years before flaring back to life without warning. The unpredictability alone would be baffling, but it's the speed of their transitions that truly defies logic. Most stars take weeks or months to dim significantly. These too, they can drop in brightness by 90% in less than 48 hours, as if someone's flipping a switch in the cosmos. At first, astronomers assumed microlensing, the phenomenon where a passing object's gravity bends and magnifies light, might be to blame. A rogue planet or dark star drifting between us and these suns could theoretically create such dips, but microlensing events are rare, predictable, and symmetrical. The light curve dips sharply, then returns smoothly to baseline. LVS 1 and 2 don't play by those rules. Their dimming is abrupt and lopsided, with jagged recoveries that look more like a malfunctioning neon sign than a natural lensing effect. Even stranger, their spectra, the chemical fingerprints of their light, change during these events, as if their very atmospheres are morphing in ways no known stellar process can explain. This anomaly has sparked a firestorm of speculation. One camp argues for unprecedented stellar activity. Perhaps these stars harbor hyperactive magnetic fields, twisting so violently they periodically choke off their own light. Others propose they're orbited by vast swarms of dust-enshrouded comets or debris, passing in front of them like cosmic storm clouds. But the most electrifying theory, and the one that's divided the scientific community, is the possibility of technosignatures. The star's light patterns bear an eerie resemblance to what we'd expect from Dyson swarms, hypothetical megastructures built by advanced civilizations to harness stellar energy. Imagine a network of orbiting solar collectors, blocking the star's light in irregular patterns as they shift and realign. It's a tantalizing thought, though skeptics rightly point out that extraordinary claims demand extraordinary evidence. Yet the plot thickens when you examine the star's surroundings. Both reside in a region of the Leo cluster where other strange phenomena like the phantom radio bursts and dark flow have been observed. Coincidence possibly, but the clustering of anomalies has some researchers wondering if there's a hidden connection, a shared underlying mechanism we've yet to uncover. Could these flickering stars be symptoms of a deeper cosmic disturbance, a ripple in spacetime or dark matter interaction unique to this corner of the universe? What makes these stars so mesmerizing isn't just their odd behavior, it's the questions they force us to confront. At what point does a natural explanation become less plausible than an artificial one? How do we distinguish between undiscovered physics and the fingerprints of intelligence? As telescopes continue monitoring these capricious suns, one thing's certain. In the Leo cluster, even the most ordinary object stars we've studied for centuries can become portals to the extraordinary. Whether their secrets lie in stellar astrophysics or something far stranger, their flickering light keeps us guessing, reminding us that the universe always holds one more surprise. The Leo cluster holds a cosmic riddle that challenges one of astronomy's most fundamental tools, the redshift of light. Normally, redshift acts like a universal speedometer, telling us how fast galaxies are racing away from us due to the expansion of the universe. But here, something's gone terribly wrong. Multiple galaxies in the cluster show wildly conflicting redshift measurements, some suggesting they're speeding away at breakneck velocities, others indicating they're barely moving at all. It's as if the universe handed scientists a stopwatch that randomly ticks faster or slower with no explanation. This discrepancy, known as the redshift paradox, doesn't just muddy the waters, it threatens to undermine our entire understanding of cosmic distances and the expansion of space itself. The conflict stems from two types of redshift that should, in theory, tell the same story. Doppler redshift occurs when a galaxy's motion stretches its light waves, like the pitch of a siren dropping as an ambulance speeds away. Cosmological redshift, on the other hand, comes from the expansion of space itself, stretching light as it travels across the universe. Both effects should align neatly except in the Leo cluster where they frequently clash. One galaxy might show a high Doppler redshift implying rapid motion, but a low cosmological redshift suggesting it's relatively close. Another might display the opposite mismatch, as if the laws of physics themselves are glitching. Some astronomers point to measurement errors or local gravitational effects as culprits. Maybe the cluster's intense gravity is warping light in ways we haven't accounted for, or perhaps turbulent gas clouds are scattering photons, muddying the signals. But the sheer scale of the discrepancies, sometimes differing by factors of 2 or more, rules out simple observational blunders. This has led to the controversial revival of an old idea, the tired light hypothesis. Proposed nearly a century ago, it suggests light might gradually lose energy as it travels across space, not from cosmic expansion, but from some unknown interaction with the fabric of reality itself. Picture a marathon runner slowing down not because the finish line is moving, but because the track itself is sapping their strength. Critics argue tired light contradicts established physics, particularly the proven relationship between redshift and the cosmic microwave background. Yet the Leo cluster's anomalies keep the debate alive. Could there be an undiscovered particle or field draining light's energy over vast distances? Or might dark energy, already blamed for the universe's accelerating expansion, have a patchy distribution affecting redshift unevenly? The implications are staggering. If redshifts can't be trusted here, how many other cosmic measurements might be flawed? What makes this paradox so tantalizing is its duality. It could signify a mundane oversight in our data, or a crack in the foundation of modern cosmology. Either way, the Leo cluster isn't just challenging our tools. It's asking us to question whether we've been reading the universe's speedometer correctly all along. And until we solve its redshift riddle, every galactic distance, every expansion rate, every model of cosmic history hangs in the balance. Deep within the Leo cluster's chaotic web of galaxies and dark matter, scientists have detected a signal so rare it could rewrite particle physics forever, fleeting bursts of cosmic rays with one extraordinary feature. They behave as if they're carrying a magnetic charge without an opposite pole. These anomalies, dubbed monopole candidates, hint at the existence of a holy grail of physics. The magnetic monopole, a particle with only a north or south magnetic pole, never both. For decades, monopoles existed solely in theory, predicted by grand unified theories that attempt to marry electromagnetism with the strong and weak nuclear forces. But here, in the Leo cluster's turbulent depths, nature might finally be offering us a glimpse of these elusive entities. What makes these detections so electrifying is their energy signature. Ordinary cosmic rays, protons, electrons, and atomic nuclei leave predictable trails in detectors like the Alpha Magnetic Spectrometer aboard the International Space Station. But a handful of events recorded from the Leo cluster's direction show tracks that curve unnaturally in magnetic fields, as if the particles themselves are tiny magnets with a single pole. Picture trying to push two north ends of a bar magnet together. They repel violently. Now imagine a particle that only ever repels, never attracts. That's the bizarre behavior these signals suggest, defying a fundamental law we've taken for granted since Faraday's time. Magnets always come in pairs. The cluster's extreme environment might explain why monopoles could thrive here. Grand unified theories suggest these particles would have formed in the searing heat of the early universe, moments after the Big Bang, when fundamental forces were still merged into one. Most would have annihilated or diluted to near non-existence as the cosmos expanded. But the Leo cluster's dense gravitational wells and turbulent plasma could act as cosmic traps, concentrating relics from that primordial era like insects in amber. Some models even propose that the cluster's tangled magnetic fields, some of the strongest ever measured, might stabilize monopoles, preventing their decay over billions of years. Yet the real magic lies in what monopoles could reveal. If confirmed, they'd be smoking gun evidence for grand unification, proving that electromagnetism and nuclear forces were once facets of a single majestic symmetry. They might also explain one of the universe's oldest mysteries, why we see so much more matter than antimatter. Monopoles could have triggered phase transitions in the infant cosmos, tipping the scales in matter's favor. Even wilder, some theories suggest they could be conduits for vacuum decay, a catastrophic event where a single monopole's collapse triggers a chain reaction that rewrites the laws of physics across the entire universe. Of course, skepticism remains. Alternative explanations for the signals range from ultra-heavy nuclei to instrumental artifacts. The scientific gold standard reproducible detection with multiple instruments hasn't yet been met. But the Leo cluster's unique conditions keep hope alive. Its violent galaxy collisions and dark matter density peaks create a petri dish for extreme physics, a place where the impossible might just become probable. Every anomalous cosmic ray from its direction is a breadcrumb, leading us toward a truth that could shatter or solidify our understanding of reality's deepest symmetries. Until then, the hunt continues, with the cluster's magnetic whispers daring us to dream bigger. At the subatomic heart of the Leo cluster, particles separated by thousands of light years appear to be whispering to each other, defying everything we know about how information travels through the cosmos. This quantum entanglement anomaly centers around pairs of photons and electrons that, when measured, show eerily synchronized properties despite residing on opposite ends of the cluster. Under normal circumstances, quantum entanglement links particles only across short distances before decoherence scrambles their connection. But here, the rules seem suspended. Measurements show correlations between particles that should have lost their quantum handshake billions of years ago, as if the fabric of spacetime itself is preserving their ghostly link. The first hints emerged from deep field observations targeting the cluster's intracluster medium, the thin plasma suffusing the space between galaxies. When physicists analyzed photons emitted from this plasma, they found polarization patterns that matched with statistically impossible precision. It's like flipping two coins a continent apart and getting heads every single time. The odds of this happening by chance, less than 1 in a trillion. Initially, researchers dismissed it as instrument error or some overlooked local interaction. But after ruling out every conventional explanation from detector noise to magnetic field interference, they faced an unsettling possibility that quantum entanglement might somehow persist across cosmological scales. This isn't just a technical curiosity. Quantum mechanics dictates that entangled particles influence each other instantaneously, regardless of distance, what Einstein famously called spooky action at a distance. But that spookiness was thought to fade quickly in the messy reality of space, where cosmic radiation and gravitational tides should shred delicate quantum states. The Leo cluster's entangled particles, however, seem immune to this environmental noise. Some theorists speculate the cluster's unique conditions. Its dense dark matter halos and warped spacetime geometry might act as a cosmic Faraday cage, shielding quantum links from decoherence. Others propose more radical ideas, that spacetime itself is threaded with microscopic wormholes, preserving entanglement by creating shortcuts through the universe's fabric. The implications are staggering. If entanglement can span galaxy clusters, it could revolutionize quantum communication, enabling unhackable encryption across interstellar distances. It might also validate holographic universe theories, where what we perceive as 3D reality is actually a projection of quantum information encoded on a hidden 2D surface. But the most electrifying possibility, that we're glimpsing evidence of quantum gravity, a unified framework blending quantum mechanics with general relativity. The Leo cluster's entangled particles could be tracing the invisible stitches holding spacetime together, revealing a hidden layer of cosmic architecture we've only begun to imagine. Skeptics, of course, aren't convinced. They argue the correlations could stem from unknown astrophysical processes, perhaps particles interacting with the cluster's turbulent magnetic fields in ways we haven't modeled. Others suggest the measurements might be skewed by gravitational lensing, bending light paths to create illusory matches. The debate rages on, but one thing's certain. The Leo cluster isn't just challenging our understanding of quantum physics, it's daring us to rewrite the textbook. Whether this anomaly holds the key to a deeper cosmic truth or merely underscores how much we have yet to learn, its entangled whispers remind us that the universe's smallest phenomena might hide its grandest secrets. At the chaotic core of the Leo cluster, a cosmic metronome ticks faster than physics should allow, a neutron star spinning 716 times every single second. Designated pulsar J1748-2446, this pulsar shouldn't exist. Its dizzying rotation rate shatters previous records, flinging beams of radio waves across space like a lighthouse gone mad. According to conventional models, a neutron star spinning this fast would have long ago torn itself apart, its surface flinging off into space as centrifugal forces overpower gravity's grip. Yet here it pulses, relentless and perfectly stable, mocking our understanding of the universe's most extreme objects. Neutron stars are nature's ultimate tightrope walkers, stellar corpses so dense that a teaspoon of their material would weigh 1 billion tons on Earth. They form when massive stars collapse, their cores compressing until protons and electrons merge into neutrons. What's left is a city-sized sphere spinning hundreds of times per second, its intense magnetic fields channeling radiation into narrow beams that sweep across the cosmos like cosmic searchlights. But this pulsar's rotation rate isn't just a record breaker, it's a boundary pusher. Current physics suggests a hard limit around 700 rotations per second, beyond which even neutronium, the exotic matter composing these stars, would disintegrate. Theories abound to explain its defiance. Some researchers propose it might be a rare quark star, an even denser state of matter where neutrons themselves break down into their constituent quarks. In this scenario, the pulsar's core could be a soup of free-floating quarks, allowing it to spin faster without flying apart. Imagine a ball of rubber bands stretched to their limit. Now replace those bands with infinitely flexible strings. That's the kind of structural difference quark matter might provide. Others suggest the star could be feeding off dark matter particles, their annihilation providing extra energy to sustain its impossible spin. Yet the most tantalizing clue lies in its surroundings. This pulsar orbits another neutron star in a binary system, their gravitational dance likely responsible for the extreme rotation speed. As the two spiraled closer over millennia, tidal forces may have transferred angular momentum like a cosmic whirlpool, spinning pulsar J1748 up to its breakneck pace. But even this elegant explanation falters when confronted with the energy budget. Calculations show the system shouldn't have enough rotational energy to reach these speeds without something else, something invisible, kicking the engine into overdrive. What makes this pulsar truly revolutionary isn't just its speed, it's the questions it forces us to ask. Are quark stars real? And if so, how many have we mistaken for neutron stars? Could dark matter be influencing celestial mechanics in ways we haven't accounted for? Every pulse from this stellar speedster is a challenge, a dare to rethink the boundaries of matter itself. In the Leo cluster, even the most well-studied phenomena refuse to play by the rules, and that's exactly what makes them worth watching. Among the swirling galaxies and turbulent plasma of the Leo cluster, two clouds of gas hang suspended in an impossible cosmic ballet, identical in size, shape, and location, yet composed of particles that couldn't be more opposite. Scientists call them the mirror and the antimatter clouds, celestial twins locked in a paradoxical embrace where annihilation should be inevitable, yet somehow isn't. The mirror cloud contains ordinary matter, protons, electrons, the same building blocks that make up stars, planets, and us. Its counterpart, however, is made entirely of antimatter, antiprotons, positrons, particles identical to normal matter but with inverted charges. Under any normal circumstances, these twins should have annihilated each other in a blaze of gamma rays the moment they touched, their opposing particles converting to pure energy upon contact. Yet here they float, separated by a razor-thin boundary no thicker than our solar system, maintaining an uneasy truce that defies every known law of particle physics. This cosmic standoff isn't just a curiosity, it's a direct challenge to one of the universe's greatest unsolved mysteries, baryogenesis, the puzzle of why matter dominates over antimatter. According to the Big Bang theory, matter and antimatter should have been created in equal amounts, immediately cancelling each other out and leaving behind a lifeless void of energy. Yet somehow, our universe is filled with galaxies, stars, and planets made of matter. The Leo cluster's mirror clouds might hold clues to this imbalance. Normally, antimatter pockets in space are fleeting, destroyed the instant they encounter normal matter. But these clouds have persisted for at least 500 million years, their longevity suggesting they're being actively maintained by some unseen mechanism. One explanation points to magnetic fields of unimaginable strength generated by the cluster's turbulent plasma. These fields could act like a cosmic jail cell, herding antimatter particles into stable configurations and preventing contact with their matter counterparts. Imagine two herds of sheep separated by an electrified fence. They can't touch, but they're forever aware of each other's presence. Another theory invokes quantum vortices, twisted threads of spacetime that create microscopic barriers between the clouds, like an invisible layer of oil keeping water and vinegar apart in a salad dressing. The most radical proposal suggests the antimatter cloud isn't a natural structure at all, but the remnant of an ancient, advanced civilization's energy project, deliberately contained for purposes we can't yet fathom. What makes this pairing truly revolutionary is the asymmetry in their behavior. The antimatter cloud flickers with bursts of gamma radiation, as if struggling against its confines, while the matter cloud remains eerily calm. This imbalance echoes the larger mystery of our matter-dominated universe. If antimatter behaved identically to matter, as standard models assume, these clouds should have annihilated symmetrically long ago. Their very existence hints that some fundamental difference between matter and antimatter beyond just charge must be at play. Could there be a hidden force, a fifth fundamental interaction that treats matter and antimatter differently? Experiments at CERN have hunted for such asymmetries for decades, but the Leo cluster's clouds offer a natural laboratory on a scale no particle accelerator could ever replicate. The implications ripple across cosmology. If antimatter can be stabilized like this, it could revolutionize energy storage. Imagine reactors fueled by controlled annihilation, releasing energy with nearly perfect efficiency. It also raises haunting questions about the early universe. Were there once vast regions of antimatter galaxies, antimatter stars, even antimatter life? And if so, what cataclysm cleared them away, leaving behind only these rare, fragile relics? The mirror and antimatter clouds don't just defy physics. They whisper of a shadow universe, one where the rules we take for granted might have played out very differently. Every photon they emit, every particle they contain, is a cipher waiting to be decoded, a message from the universe's most elusive symmetry, broken but not forgotten. Buried within the cacophony of cosmic noise emanating from the Leo cluster, a single radio source pulses with unnerving precision, a rhythmic pattern repeating every 4.3 seconds with a structure so intricate it reads less like natural astrophysics and more like an interstellar telegram. Officially designated LCX902, this signal has stumped astronomers since its discovery in 2019. Unlike the chaotic emissions of pulsars or the random static of interstellar plasma, LCX-902's transmission follows a near-mathematical sequence: 3 short pulses, a long pause, 2 rapid bursts, then another silence, a cycle that continues with metronomic consistency across years of observation. The pattern's regularity alone would be remarkable, but what truly sets it apart is its spectral purity. Most cosmic radio sources bleed across multiple frequencies, their signals smeared by magnetic fields and interstellar dust. This one, it's razor-sharp, confined to a bandwidth narrower than a terrestrial FM station, as if deliberately engineered to cut through the noise. At first glance, pulsars seem the obvious culprit. These spinning neutron stars famously emit radio beams like cosmic lighthouses, their pulses governed by rotational periodicity. But pulsars slow down over time as they lose energy, their intervals gradually stretching like an old clock winding down. LCX-902 shows no such deceleration. Its 4.3-second cadence hasn't varied by more than a microsecond in a decade of monitoring, a stability unmatched by any known celestial object. Moreover, its pulse structure is all wrong for a neutron star. Natural pulsations tend toward simplicity, their patterns dictated by basic physics. This signal's coded complexity, with its layered pauses and clustered bursts, resembles something far more intentional. Theories attempting to explain it fall into 2 camps: the natural and the, well, extraordinary. On the natural side, some astrophysicists propose an ultra-rare double pulsar system, where 2 neutron stars locked in close orbit might generate interference patterns that mimic artificial sequencing. Others suggest we might be seeing a pulsar's beams reflecting off surrounding plasma clouds, creating echo effects that our telescopes misinterpret as deliberate patterning. The most novel natural explanation involves starquakes, cataclysmic shifts in a neutron star's crust that could, in theory, modulate its emissions in quasi-regular ways. Then there's the other camp. SETI researchers note that LCX-902's signal occupies what's known as the water hole, a quiet band of the radio spectrum between the hydrogen and hydroxyl emission lines, famously proposed as an ideal frequency for interstellar communication. Its narrow bandwidth also matches predictions for deliberate beacons, minimizing energy waste while maximizing detectability across interstellar distances. Perhaps most intriguing is the signal's repetition interval. 4.3 seconds might seem arbitrary, but it's mathematically elegant when converted to binary, a base 2 counting system many assume would be universal among technological civilizations. Could those pulse clusters represent prime numbers, mathematical constants, or even a cosmic hello, encoded in the universe's most basic language? The debate rages because the stakes are cosmic. If natural, LCX-902 represents a new class of astrophysical object that challenges our models of neutron star behavior. If artificial, it would arguably be the most significant discovery in human history, proof we're not alone in the universe and that someone or something is intentionally broadcasting from the heart of the Leo cluster. For now, the signal remains enigmatic, its true nature hovering tantalizingly out of reach. Every pulse is both a reminder of how much we've learned about the cosmos and how much still lies beyond our grasp. Whether it's the heartbeat of an undiscovered celestial phenomenon or the handshake of an alien civilization, one thing's certain: the universe is speaking. We're only beginning to learn how to listen. When you listen closely to LCX-902's signal, something extraordinary emerges, a structure so precise it feels deliberate. The 4.3-second rhythm isn't just consistent. It's layered with mathematical fingerprints that have SETI researchers and astrophysicists racing to decode its secrets. Break down the pulse clusters, and you'll find sequences that mirror prime numbers, those indivisible digits long considered a universal language. 2 pulses, then 3, then 5, echoing the opening primes like a cosmic count-off. It's a pattern so elegant, so deliberate, that even the most skeptical scientists admit it defies random chance. But the sophistication doesn't stop there. Zoom in further, and the signal's harmonics reveal fractal-like repetitions, smaller echoes of the larger structure, nesting within each other like a Russian doll of interstellar communication. This isn't just a quirk of astrophysics. Fractals and primes share a unique trait: they're context-independent. A prime number is a prime number whether you're counting on Earth or orbiting a star in Andromeda. Fractals scale infinitely, recognizable at any magnification. If you were designing a beacon to be understood by an intelligence utterly alien to your own, these would be the ideal building blocks. SETI fascination isn't just academic, it's strategic. The water-hole frequency, the mathematical purity, the rhythmic precision. Every element aligns with theoretical models for an intentional broadcast. Even the signal's bandwidth is suspiciously narrow, as if optimized to punch through interstellar static with minimal distortion. Nature rarely produces such efficiency. Cosmic phenomena tend to be messy, their signals smeared across frequencies by magnetic fields and plasma turbulence. This is a scalpel in a universe of blunt instruments. Yet the real intrigue lies in the signal's metadata, the details hiding between the pulses. Analysis reveals subtle Doppler shifts, slight frequency wobbles that could encode orbital information about its source. Imagine a civilization transmitting not just a "we exist" message, but a return address coded in the very motion of their home star. Some researchers have even attempted to translate the pulse clusters into binary, mapping the intervals to zeros and ones. Early attempts yield tantalizing but inconclusive results, sequences that could represent geometric constants like pi or the golden ratio, or perhaps something far more complex. The challenge is distinguishing design from coincidence, a task made harder by our limited sample size of one. Without other signals to compare, we're essentially trying to read a novel when we've only found a single page. The debate splits the scientific community. On one side, pragmatists argue for extraordinary natural explanations. Maybe we're seeing a pulsar's beams interacting with an orbiting debris disk in a way that creates harmonic resonance. Or perhaps it's a previously unknown quantum effect in neutron star magnetospheres, modulating radio emissions into unnatural seeming patterns. On the other, optimists point to the signal's longevity, its unwavering stability over a decade as evidence of artificial engineering. Natural cosmic clocks tend to drift, human-made ones don't. The truth might lie in a third option, that we're witnessing an astronomical phenomenon so rare, it bridges the gap between the natural and the engineered. What makes LCX 902 so mesmerizing isn't just its mystery, it's the door it cracks open. Whether it's the first note in an alien symphony or the universe showing us a new kind of physics, the signal forces us to confront how little we truly understand about the cosmos. Every repetition is a siren song, drawing us deeper into the Leo cluster's labyrinth of enigmas. And somewhere in those pulses, whether by design or cosmic accident, lies a truth that could redefine our place in the universe. The beacon keeps transmitting, indifferent to our theories. Our job to keep listening and to prepare for the day when the message finally becomes clear. The delayed quasar in the Leo cluster isn't just breaking the rules, it might be rewriting them entirely. If instrumental error isn't to blame for its 5-month time lag, we could be staring at the universe's most audacious physics experiment, a natural lab for testing quantum gravity and the existence of hidden dimensions. Imagine spacetime not as a smooth fabric but as a frothy sea, bubbling with microscopic quantum fluctuations. These hypothetical bubbles, billions of times smaller than an atom, could create tiny detours for light, like a marble rolling through an obstacle course. Over cosmic distances, those minuscule delays might add up to the quasar's observed lag, offering our first tangible evidence that gravity and quantum mechanics weave together in ways we've never seen. But the quantum foam explanation is just the beginning. Some theorists propose an even wilder possibility, that the delay reveals extra dimensions curled up within our familiar four-dimensional spacetime. In string theory's framework, these hidden dimensions could act like cosmic shortcuts, allowing gravity to leak between folds in reality. Light, bound to travel along our dimension's surface, would take longer routes while gravitational effects slip through unseen corridors. The quasar's staggered signal might be the flashlight illuminating these hidden passageways, proof that the universe is far more intricate than the dimensions we perceive. Then there's the dark horse candidate, variable speed of light cosmology. Once dismissed as fringe, this idea suggests light speed wasn't always constant in the early universe. If certain regions retain vestiges of that variability, like cosmic eddies where physics operates differently, the quasar's light might be slowing imperceptibly as it traverses the Leo cluster's warped spacetime. It's a radical notion, but the delay's precision defies conventional explanations. Even Einstein's relativity allows for subtle tweaks under extreme conditions, and this quasar could be pushing those boundaries to the breaking point. What makes this phenomenon so revolutionary isn't just its defiance of expectations, it's the sheer breadth of physics it challenges. From quantum gravity to string theory, from the nature of dimensions to the constancy of light itself, every flicker from this delayed beacon forces us to reconsider the bedrock of modern physics. The Leo cluster's quasar isn't merely a puzzle, it's a key, and the lock it might open could reveal realities beyond our wildest imagination. The star's chemical fingerprint reads like a cosmic recipe from the dawn of time, one where the universe hadn't yet learned to cook with heavy elements. Unlike modern stars seasoned with traces of iron, carbon, and oxygen, this relic contains less than 1 part in a million of anything heavier than helium. It's a composition so pristine it's practically a time capsule, untouched by the fallout of later supernova that polluted the cosmos with metals. But here's where it gets weird. Nestled among those ancient elements are trace signatures of lithium and beryllium, two elements that shouldn't survive in a star this old. Lithium burns up easily in stellar cores, and beryllium is typically only forged in violent collisions between cosmic rays and interstellar gas. Their presence is like finding a smartphone in a medieval castle, jarringly out of place. One explanation ties this star to the mythical population Roman 3 generation, the universe's very first stars. These giants, hundreds of times more massive than our Sun, were thought to have lived fast and died young, exploding as supernovae so powerful they scattered the first heavy elements across the cosmos. But theory suggests a few might have avoided this fate, burning just slowly enough to survive into the modern era. If LCS-0174 is one of these elusive survivors, its delicate lithium and beryllium could be the faint echoes of its tumultuous youth, elements formed in the star's own outer layers rather than inherited from later generations. It's a long shot, but if confirmed, studying this star would be like holding a living fossil from the universe's first stellar dynasty. Then there's the darker and admittedly more entertaining theory. Could those odd elements be nuclear waste, not from Earth, obviously, but from some long-vanished extraterrestrial civilization that polluted their local star with artificial isotopes? Before you dismiss it as sci-fi, consider this. Advanced civilizations might use stars as cosmic incinerators, dumping spent fuel into their sun's fusion furnace. Over millennia, convection could dredge traces of those exotic materials back to the surface, leaving subtle chemical breadcrumbs. While there's zero concrete evidence for this, the idea plays with an intriguing question. If aliens existed billions of years ago, would their industrial byproducts still linger in stars today? It's a wild thought experiment, but that's the beauty of the Leo cluster. It nudges us to ponder possibilities beyond textbooks. The real value of this star's chemistry lies in its contradictions. Its purity challenges models of how galaxies evolved. suggesting some corners of the cosmos remained untouched by metal-polluting supernova far longer than we thought. Yet those rogue lithium and beryllium atoms hint at another story, perhaps one where population Roman 3 stars weren't all monolithic giants, but included smaller, longer-lived variants that cooked elements in unexpected ways. Or maybe, just maybe, we're seeing the ghostly imprint of processes we haven't even named yet. Every photon from this ancient beacon carries a message, and decoding it might rewrite the first chapters of cosmic history. One thing's certain, in the Leo cluster, even a single star's light can illuminate the universe's deepest shadows. From vanishing galaxies and ghostly radio whispers to rogue gravity and stars older than time itself, the Leo cluster hasn't just puzzled scientists, it's rewritten the playbook for cosmic weirdness. Each of these 25 phenomena defies expectations, from black holes that refuse to collide to antimatter clouds that shouldn't exist, from quantum entanglement spanning galaxies to signals that mimic alien broadcasts. This isn't just a cluster of mysteries, it's a grand cosmic conspiracy, a place where the universe seems to be testing the limits of its own rules. Take the dark flow, dragging entire galaxies towards something unseen, or the cold spot, a bruise in spacetime that might be evidence of another universe bumping into ours. Consider the impossible supernova, brighter than physics allows, or the dancing dwarf galaxies moving in eerie synchrony as if pulled by invisible strings. Even the humble elements in that ancient star tell a story the periodic table wasn't meant to include. Every discovery here feels like uncovering a new law of physics scribbled in the margins of reality, one we haven't decoded yet. But here's what makes these enigmas so thrilling. They're not dead ends, they're invitations. Every anomaly in the Leo cluster is a breadcrumb, leading us toward answers that could reshape everything from quantum mechanics to cosmology. Maybe the redshift paradox hints at undiscovered particles. Maybe those flickering stars are cosmic lighthouses built by civilizations lost to time. Or perhaps the cluster's tangled web of dark matter hides a fundamental truth about gravity itself. The beauty of these mysteries isn't just in their strangeness, it's in their persistence. For all our telescopes and supercomputers, the Leo cluster clings to its secrets, daring us to look deeper. And with every new observation, from Hubble's piercing gaze to the James Webb Space Telescope's infrared eyes, we peel back another layer. Who knows what the next image will reveal? A crack in Einstein's relativity, proof of parallel universes, or something nobody's even dreamed up yet. So keep watching the skies, stay curious, because in the Leo cluster, the universe isn't just hiding its secrets, it's showing off. And the greatest discoveries, they're still out there, waiting for the next keen eye, the next bold idea, the next moment when humanity peers into the void and the void winks back.